Hello everyone. Today we will be discussing quantization as well as the quantum theory, and we will go into depth about things like black bodies, black body radiation, as well as the ultraviolet catastrophe, and towards the end of this tutorial we will go over a few questions that involves Planck's equation. So the first thing that we will touch on is the quantum theory. And the quantum theory is a theoretical basis of modern physics that explains the nature and behavior of both matter and energy on the subatomic and atomic level. The nature and behavior of matter and energy at this level can be referred to as quantum physics as well as quantum mechanics. So now we're going to move on to black body radiation, and this is when certain objects are called black bodies because they emit electromagnetic radiation of all wavelengths. And black body radiation is a thermo-electromagnetic radiation within or surrounding a body in thermodynamic equilibrium with its environment being emitted by a black body. And black body radiation has a specific spectrum of wavelengths that are inversely related to the intensity that depends only on the body's temperature, which is assumed to be uniform and constant. Continuing on the topic of black body radiation, the thermal radiation spontaneously emitted by many objects can be approximated as black body radiation. And some examples of black bodies and black body radiation are objects like the sun and some stars, an oven, and the element of a toaster. And these are just some examples of black body radiation. So this distribution of a black body does not depend on the material, but only on the temperature, with a particular wavelength that is emitted with a maximum intensity shifting left as temperatures increase. This maximum will move into the visible spectrum at around 400 Kelvin and above. This explains why very hot objects glow, like the sun and the stars, and this is because objects at these extremely high temperatures emit a lot of visible light. For instance, the human body only emits around 310 kelvins, which is why we cannot see each other in the dark. The problem with the black body spectrum was that classical electromagnetism could not account for it. There were mathematical models attempting to produce these distributions, which were only able to fit the data for the longer wavelengths. But what they did not expect was for the UV portion of the spectrum to dip to the left. Instead, what they predicted was the intensity would continue increasing as the wavelength decreased, becoming infinitely large as the wavelength was approaching zero. We know this is incorrect because every time you would use a toaster or an oven, you would get blasted with UV radiation. This conflict was called the ultraviolet catastrophe. In science, a theory that does not accurately line up with the observation must be revisited and revised. Therefore, physicists and scientists realized that the classical theory must be incomplete. Then came along a physicist named Max Planck who solved this problem by introducing a theory and an idea called quantization. Max Planck, who was a German physicist, discovered many things. One of the things he discovered was why radiation from a glowing body changes color. And Planck also found that by making the assumption that energy existed in individual units in the same way matter does, rather than just as a constant electromagnetic wave, he called this quantization, and this discovery of quantization opened up a whole new world for physicists, leading to further discoveries like quantum physics. Now going more into depth about Planck's discoveries, what Planck proposed for quantization was that the vibrational energies of the atoms were quantized. This means that rather than being able to take on any value from a continuous series, like classical physics had stated, they can only possess a specific discrete value from a set of accepted values. In this way, Planck was able to come up with an idea which is now known as quantum physics, and he was able to develop an equation for black body radiation. So now we're going to talk about Planck's constant and Planck's equation. And the equation that Planck came up with for black body radiation is E equals nh nu, where E equals energy in joules. N is a positive integer, which is what results in quantization. H is Planck's constant, and it is 6.626 times 10 to the negative 34th power joules times seconds. And frequency. So the first question we will go over asks, copper emits a blue light of 450 nanometers when heated. What quantum of energy is emitted? So for this question, we're going to use a variation of Planck's equation, which is delta E equals Planck's constant times the speed of light over wavelength, where delta E is, that's what we're trying to solve for, but we know H equals 6.626 times 10 to the negative 34 joules times seconds. C, speed of light, which is a constant as well, is 2.998 times 10 to the 8th power. And this is in meters per second. And then we have the wavelength, which is given at the top here, 450 nanometers. And one problem that we noticed about what we have so far is we're working with two different units. We're working with meters and we're working with nanometers. So we're going to go ahead and convert the nanometers into meters, and that's going to give us 4.5 times 10 to the negative 7th power meters. So that's our that's now what we're going to work with for the wavelength. So now we can put this into the equation. So we have delta E equals 6.626 times 10 to the negative 34th power joules times seconds, and this is going to be multiplied by 2.998 times 10 to the 8th power meters per second, all over the wavelength, now in meters, which is 4.5 times 10 to the negative 7th power meters. So first thing we're going to do is we're going to cancel our units. Seconds cancel, meters cancel, and we're left with joules. So what we get from this is delta E equals 4.41 times 10 to the negative 19th power in joules, and that's going to be our final answer.